Good morning, everyone. I'm Ning Zhang, a PhD student at University College London, and I'm glad to present this work in collaboration with Professor Paolo Baldal and Professor Francesco Ranzato, both from University of Padova. Let's start from the motivation that inspired us. In program analysis, given a property of interest, the verification dream is an algorithm that, for all possible programs, it answers after a finite amount of time, either yes, if the given program satisfies the property, or no, if the program does not satisfy the property. And the fundamental question in commutability theory is to say whether such algorithm exists. In this case, we say that the property is decidable, otherwise the property is undecidable. There are many negative results in literature, but the very most of them refer only to the undecidability of the so-called extensional properties. An extensional property of program depends only on the function computed by the program themselves. In other words, such properties check only for the input-output behavior of the programs. One of the most remarkable results in literature is the Rice theorem, which states that every non-trivial, that is not always true and not always false, extensional property of programs is undecidable. Let's see a simple instantiation of Rice theorem. Consider the apparently simple property of computing the constant function 1. This is clearly an extensional property, since it depends only on what the program computes, that is, its input-output behavior, and furthermore, the property is non-trivial, since clearly exist programs that compute 1 and other programs that do not compute 1. And thus, by Rice theorem, one can conclude that no algorithm can decide for all programs whether it is computing the constant function 1. Besides extensional properties, which are undecidable, several non-extensional properties are of utmost importance in the practice of programming. For instance, deciding program invariance. More in general, intensional properties depends on the program shape, that is, how the program is written rather than what it computes. Hence, these properties are the main focus of program analysis. We also note that approximation of extensional properties are intentional. In fact, since programs with the same input-output behavior may be classified differently depending from some heuristics. An approximation can be either unsound, that is, both false positive and false negative are admitted, and this does not give any guarantees. In fact, if an algorithm returns a positive output, we cannot distinguish whether it is a true or a false positive. And as pointed by Patrick Cuseau, this approach is clearly not for scientists. The sound approach consists of allowing either false positive or false negatives, so that one of the two possible answers gives certain information. As example of sound approximation, consider the case we allow only false positives. This means that when the output of the algorithm is no, we know that it is a true negative, while when the answer is yes, it corresponds to an unknown answer, since we do not know whether it is a true or a false positive. On the other hand, we can take into account intensional properties by considering abstract semantics of programs rather than the input-output semantics of them. For instance, we see here two programs implementing respectively insertion sort and merge sort, and despite computing the same function and thus having the same extensional properties, the two programs differ for many intensional properties. For instance, we can take as abstract semantics the number of lines of code, and note that deciding the number of lines is clearly a decidable property. Other semantics of interest are the ones related to the time and space complexity of the programs, or for instance, how many functional calls occur, or decide whether a certain variable is constant. Let's have a look at some related work. A first generalization of classical extensional results into an intensional setting has been put forward by Esperti. who has extensively investigated the so-called complexity clique, which are sets of programs closed with respect to the extensor behavior and the complexity class. In particular, they show unstability results of the complexity clique. A different approach has been explored by Moyen and Simonsen, where the classical notion of extensionality has been weakened in order to take into account over-approximation of extensional sets. This allows, for instance, to show that every decidable over-approximation of extensional sets contains infinitely many false positives. Let's see some examples. Given a program P, a non-extensional property could be to ask whether the program computes a sorting function and up to a quadratic complexity. The result of Asperti allows to conclude immediately that there is no algorithm that decides such property. Moyen and Simonsen further generalize the result, and in particular they consider sound over-approximation of such property. Hence, when the output of the algorithm is yes, we cannot distinguish whether it is a true or a false positive. And what they show is that among those false positives, there must be at least one program for each function and complexity class. For instance, subsolvers or even very bad sorting algorithms. Let us now introduce our work. Our aim is to provide a Rice theorem for intensional properties, dealing with general abstract semantics representing the properties of interest. As assumptions, we have a Turing-complete model, that is, a computation model that can simulate any other Turing machine. And second, we will use a bijective Gödel number. This will allow to refer to programs by simply referring to the index. We use the symbol phi to refer to the input-output semantics of a program, which is a partial function, and this allows to write an enumeration of recursive function simply by enumerating the programs. Let's introduce our framework. An abstract semantics is a pair where the first component is a function pi that associates program indices to a function. And this function represents the property of interest of the program. The second component is an equivalency relation, which allows to further abstract and compare programs with different semantics, and this is necessary to show that certain properties of abstract semantics hold. We also note that every abstract semantics induces an equivalence between programs, which we refer to as the induced equivalence of the abstract semantics. The equivalence holds whenever two programs have equivalent abstract semantics. Let's see some examples of semantics. The concrete semantics has as first component the function that maps each program with its parser function, the program compute. And as semantics equivalence, we can take the equality between functions. Second, the asymptotic complexity semantics can be seen as a semantics where the first component is a Bloom complexity measure, which can be, for instance, the number of steps performed by the computation model. And as semantics equivalence, we can take the one that considers two complexities equivalent if they have the same asymptotic behavior. Third, we show that the complexity clique of Asperti can be included in our framework by considering a function that returns the encoding of a pair. The concrete semantics function as the first component of the pair, and then the complexity of the program. And then we say that the two semantics are equivalent if and only if they have equal concrete semantics and equivalent asymptotic complexity. Let us introduce the first property of semantics that we are going to consider. An abstract semantics is called fair if there exists an abstract universal program U that takes as first argument an index of a program A that we simulate, and then some other inputs. Then the program U simulates the program A with the remaining inputs, and we require that such simulation preserves the abstract semantics. We point out that the notion of fairness has been introduced first by Asperti, but differently from him, here we ask for a program that behaves as an interpreter and preserves the abstract semantics, and not necessarily the concrete semantics. The second property is the strongest known property. First, let's recall the standard semantic theorem, which informally states that for any program A and two vectors x and y, there exists a computable transformation that, given the initial program A and the vector x, returns a new program. And this program has the same input-output behavior, except for the fact that the input x is fixed. And this amounts, roughly speaking, to a program that hardcodes the input x and executes the original program. Our generalization for abstract semantics is slightly stronger and requires that there exists a computable transformation that takes an additional argument b, and then returns a new program where the computation of the program b on input x has been fixed. In unit, we require that the abstract semantics is preserved. As example, we preview semantics are very strong SMN and intuitive because executing a fixed program requires constant complexity. Now we present our intentional version of clean cycle recursion theorem, given a total computable function h that transforms indices of programs into indices of programs, and given an equivalence relation induced by very strong SMN semantics, we have that there exists an index of our program which is a fixed point of h. Let us show an example. We may wonder whether there exists a program transform, or better, a total computable function which modifies the asymptotic complexity of every other program, even without preserving the input-output behavior. And the answer is no. In fact, by using our second recursion theorem, there must exist an index of a program n that is equivalent to the modified program h of n. And this means that the function h cannot alter the asymptotic complexity, at least of the program n. Now, let us explain some of the notation introduced first by Moynihan and Simonsen. Given an equivalence relation between indices of programs, we say that a set of indices is extension, according to the equivalence relation, if it is a union of equivalence classes. Then we say that the set is partial extension if it contains at least one equivalence class, as shown in the diagram. Then we say that the set is universal extension if it contains at least one program for each equivalence class. The second recursion theorem presented can be used to derive our intentionalized theorem, which statement is the following. Given a fair and strong SMN semantics, every set A that is partial extension and not universal extension, according to the induced equivalence, is not recursive. Let's see a graphical representation. Here the requirement of partial extensionality and not universal extensionality amounts to require two equivalence classes of programs. One must be a subset of A, and the other one must be disjoint with respect to A. For instance, let's take into account the Hadi set K of program X that terminate in their own input X. And this set is not extension, since it depends also from the code of the program X. And one can take the complete semantics and note that the equivalence class of programs computing the constant zero function, for instance, since it always terminates, it is included in K, so that the set K is partial extension. And moreover, the equivalence class of programs that compute, for instance, the always divergent function has clearly no intersection with k. So it is disjoint respect to k. And this allows to conclude immediately with our nice theorem that k is non-recursive. Similarly, we can instantiate the result for the set of programs that compute a sorting function in n log n, which is a complexity clique in the sense of asperity. We can take into account the complexity clique semantics and note that the equivalence class containing good implementation of merge sorts is clearly a subset of A. And then the equivalence class that contain implementation of insertion sorts is clearly disjoint with respect to A. So that the set A must be non-recursive due to our Rice theorem. Let us show another example. Consider a case we are interested in designing a static verifier recognizing a set of programs P. A static verifier is a total computable function that takes as input an index of a program and then it outputs either 0 or 1. And we also say that the verifier is sound if it will not output false positive. That is, when the output is 1, the input program satisfies P. The first question is asking whether we can construct a sound verifier, for example, for the set of programs running in at least cubic time. And in this case, the answer is clearly yes. In fact, we can take as sound verifier the always constant 0 function, which is a total computable function, and it also satisfies the soundness condition vacuously because the premise is false. A more interesting question is how good can be the sound verifier. More precisely, we hope that among those false negatives, we can exclude some very bad programs. For instance, programs running in exponential time. Let's take into account the set of positive outputs, that is the set of programs for which the verifier outputs 1, and the set of negative outputs, that is the set of programs for which the verifier outputs 0. By soundness, the set of positive outputs must be a subset of P, and this is equivalent to say that the complement of P is a subset of the set F. Hence, for instance, all the programs that run in constant time must be a subset of F. And this implies that F is partially extension. Now, what we hope is that, for instance, programs running in, say, 2 to n complexity are not in the set. In other words, we want that the set F is not universally extensional. However, by our Rice theorem, if this is the case, then F would be a non-recursive set. And this is clearly a contradiction because the verifier is itself computable. And this implies that among those programs for which our verifier will output 0, which ideally should represent programs that runs in less than cubic time, we will have programs for each possible class of complexity, including exponential time programs. Now, let us show a different approach. A result of Moyen and Simonsen is that a Rice theorem can be obtained by considering equivalence relations admitting so-called intricated switching families. What we do is to define two properties of abstract semantics that, together with the strong SMN property, allows to use the result of Moyen and Simonsen, which in turn implies an intentional version of Rice theorem. The first property we consider is the branching, which informally represents the possibility to model conditional statements with only equality guards, but not necessarily inequality guards. Second, we say that a semantic is discharging if arbitrary fresh variables can be added without altering the semantics. A second version of Rice theorem that can be obtained using also the result of Moyen and Simonsen is the following. Given a branching, discharging, and strong SMN semantics, If a set is partially extensional and not universally extensional according to the induced equivalence, then the set is not recursive. Let us show a possible application. We consider control flow graphs, which is a basic structure in plugin analysis, and it is widely studied in research, for instance by Muller-Owen and Seidel, Warrer, Wachnine, and so on. Properties of control flow graphs depend from the computational power of the model. In our case, we consider basic affine control flow graphs that, as shown in the figure, can have multiple edges, and these edges can be either affine variable updates or equality cards. This means that we cannot check, for instance, whether two variables are not equal. We first have proved that the basic affine control flow graphs, even without inequality guards, are a Turing-complete computational model. Then we have defined the so-called state semantics, which checks for a given predicate whether the connecting semantics of a control flow graph satisfies such predicate. In particular, we show that the state semantic satisfies the branching, the strongest man, and the discharging properties, and this clearly allows to apply our nice theorem. As example, we can consider as predicate any hyperproperty, that is a set of sets of states, and then we define two sets. One takes into account the set of graphs, such that for all inputs the collective semantics of the graph satisfy the given hyperproperty. The other one requires only the existence of at least one input, such that the semantics satisfy the hyperproperty. And then we can show as a corollary of our race theorem that if the hyperproperty is not trivial, that is, if it is not always true or not, and not always false, then both sets are not recursive. Let's see an instantiation of the result. We can take as hyperproperty the set of sets of states where a certain affine variant holds. Then the unstability of the universally quantified set entails exactly the problem of deciding whether a certain affine programming variant holds. A result that has been previously proved by Muller-Owen and Seidel through a reduction to the post-correspondence problem. We also point out the fact that by removing completely the guards, that is considered unguarded control flow graphs, deciding affine programming variance would be decidable due to Carr's algorithm. Let us summarize our work. As contribution, we have provided an abstract semantics framework that generalizes, for instance, Green's second recursion theorem and the theorem of aspecting, and then we have established a precise connection with the work of Moy and Simonsen. As future work, we would like to generalize the intentional Rice-Peirce theorem, and second, we would like to investigate abstract semantics defined by abstract interpretation of programs, perhaps by taking into account more about the syntax of programs, rather than focusing on Gödel numbering. And then, finally, our result relies on the assumption of Turing completeness and cannot work out in a subrecursive setting, and extending abstract semantics in a subrecursive setting seems a challenging task, and perhaps with a lower computational power one may also hope to achieve positive results. Thank you for your attention.